Okay guys, so now we're going to talk about number e, and this is the most important number in human history, except possibly for 0 and 1, and I will start out where I left off last time. So I'm going to look at the series sum of 1 over n factorial. N goes from 0 to infinity. So the series 0 factorial is equal to 1. So the series look like this: 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus etc. Okay, so first of all I want to say that this series converges, and let me repeat the proof that I gave you last time. Notice that if I compare the series 1 plus 1 plus 1 over 2 factorial plus 1 over, so what's the 3 factorial? 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4 plus 1 over 1 times 2 times 3 times 4 times 5, etc. And if I compare this series to the series 1 plus 1 plus 1 half plus 1 over 2 square plus 1 over 2 cube plus 1 over 2 to the 4 plus etc., you would agree with me that this term is actually equal to this term, but this term is lesser equal than this term, because this is 1 divided by 2 times 3 and this is 1 divided by 2 times 2, etc. So all these terms are lesser equal than appropriate terms of this series. Now this is a geometric series with the radius r over the equals to 1/2, and therefore by previously proven theorem this series converge. And since the term of this series are lesser equal than the term of this series, we conclude that this series 1 over n factorial, and from 0 to infinity, converges. And if it converges to a number, then this number has a name, and the name of this number is e. As I said before, this is the most important number in human history, with a possible exception of 0 and 1. The E stands for Euler. This is one of the most famous mathematicians of all time, and I will be the last guy in the world to ever teach you how to pronounce word, but please pronounce his name Euler and not Euler. It's just terrible. So the name is Euler and the number E is named after him. Alright, so this is the definition of a number E. Now probably from calculus you know another definition of number e, and this is 1 plus 1 over n to the power n, and as I told you so many times before, limit of this sequence. And as I told you so many times before, the fact that the sequence converges is absolutely not clear because we don't know what the number e is, but what I want to prove now is that the limit of this sequence 1 plus 1 over n to the power n converges to the same number e, which is equal to the limit of the partial sums of the series 1 over n factorial and from 0 to infinity. And now we will start working on a proof of this fact. All right? Okay. Are you ready? Okay, so let me say that Tn is equal to 1 plus 1 over n to the power n, and let me say that Sn is equal to the partial sum of the series n from 0 to Sm. M from 0 to m 1 over n factorial. All right? And what I want to do is I want to show that this sequence Tn and this sequence Sm converges to exactly the same number. In other words, I want to show that the Tn's are somewhere between the limits of Sm and the limit of Tn. So I want to show that Tn and Sn, as n and m get very, very large, are not too far from one another. Okay, so the first part is I'm going to deal with the series. Let me do a new page. I'm going to deal with this. So let me remind you here that Sn is equal to sum of 1 over k factorial, k from 0 to n. Okay. And now I'm looking at Tn, which is 1 plus 1 over n to the power n. And I'm going to use the binomial formula. So we know that a plus b to the power n is equal to the sum of a to the power n minus k, b to the power k, and then I have to multiply it by the binomial coefficient and choose k. Okay, so let's deal with 1 plus 1 over n to the power n, and let's write it down. So the first term here will be 1, the next term will be 1 times 1 over n, agree? The next term will be n choose 2 times 1 over n square, and then you will have n choose 3 times 1 over n cube plus n choose 4 times 1 over n to the power 4 plus etc. Do you agree with me so far? Okay, cool. So let's do it one more time. You will have 1 plus 1 times 1 over n plus, so n choose 2 is n times n minus 1 divided by 2 factorial divided by n squared. Good. And then I will have, yeah, this is n here. And then I will have n choose 3, so it will be n times n minus 1 times n minus 2 divided by n cube. And then I also have to divide it by 3 factorial. Okay, let me do one more, n times n minus 1 times n minus 2 times n minus 3. So that's divided by 4 factorial and n to the power of 4. Okay, so plus etc. So let me rewrite it in a form. This is n again. Let me rewrite it in the form of 1 plus 1, and then I will have 1 over 2 factorial. So I'm factoring out the 2 factorial, and then I will have n times n minus 1 over n squared, which is n times n, and then I will have 1 over 3 factorial n times n minus 1 times n minus 2 divided by n cube, and I will go on like that. So in general I will have 1 over k factorial times n minus 1, n minus 2, etc., n minus k plus 1 divided by n to the power k. Now let me simplify this expression further. So let's see what happens with this term. You will have 1 plus 1 plus 1 over 2 factorial times, I divide the first n by the second n, I will have 1, and when I divide n minus 1 by this n over here, I will have 1 minus 1 over n. True? Okay. So now I will go with 1 over 3 factorial, and now I will do the same thing. This is the quantity divided by n cubed, so if I divide this n by one of those n's, I will have 1, and then I will have, when I divide n minus 1 by n, I will have 1 minus 1 over n, and then I will have 1 minus 2 over n. And so in general, if I go on like that, I will have plus 1 over k factorial times 1 minus 1 over n, 1 minus 2 over n, etc. 1 minus k over n, and so the last term will be 1 over n factorial times 1 minus 1 over n, 1 minus 2 over n, etc. And the last term will be 1 minus n minus 1 over n. Okay, so this is the way I'm writing down this particular term, 1 plus 1 over n, and if I look at it very, very carefully, I will immediately see that this number is less than 1, and this number is less than 1, and this number is less than 1, etc. So each number in those products is less than 1, and so my conclusion is that this quantity is less or equal than 1 plus 1 plus 1 over 2 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus etc. plus 1 over k factorial plus etc. plus 1 over n factorial, which is nothing else but the partial sums Sn for my series 1 over k factorial. Okay, you agree with that? So my conclusion is that these numbers, 1 plus 1 over n, they're bounded. They're less or equal than the numbers Sn. Right? And what that means is that I don't know yet whether the limit of Tn exists or not, but what I can say is that the lim sup of Tn, it always exists, and so the lim sup of Tn is less or equal than the lim sup of Sn, and of course the lim sup of Sn is equal to the limit of Sn, and this is just equal to E. So my immediate conclusion is that the lim sup of Tn is less or equal than E. Let me record it on the next page. So remember that Tn was 1 plus 1 over n to the power n, and the lim sup of Tn is less or equal than E, and we're halfway done. So what are we going to do next? Well, let's look at this thing again. So remember that we wrote down Tn in a form of 1 plus 1 plus 1 over 2 factorial times 1 minus 1 over n plus 1 over 3 factorial times 1 minus 1 over n times 1 minus 1 over 2 over n plus etc. plus all the way to 1 over n factorial 1 minus 1 over n etc. product 1 minus n minus 1 over n. Alright, so this is my Tn. Now let's suppose that I'm going to stop this series at some point m. So instead of taking all the terms of the series, I will just take the first m terms of the series, okay? In that case, the Tn, because I'm adding something, so I'm taking this mth term here, 1 over m factorial times 1 minus 1 over n times 1 minus 2 over n, etc. And if I add something more to it, I'll only get it bigger. So my conclusion is that Tn will be greater or equal than 1 plus 1 plus 1 over 2 factorial times 1 minus 1 over n. And so the last term here will be 1 over m factorial times 1 minus 1 over n times 1 minus 2 over n times 1 minus m minus 1 over n. Okay. So this is a trick. I am now introducing two different indices, Tn with n and m, and let me see what happens if I'm keeping m fixed. So let's suppose that m is a fixed number, once and for all, like a million. In that case, if n tends to infinity, then all of those numbers will tend to 0, or to 1. Agree? Because 2 over n, m minus 1 over n, tends to 0, because m is a fixed number. So my conclusion is that if n tends to infinity, then Tn will be greater or equal, the limit of Tn will be greater or equal than this thing. And in fact, I'm going to say even more, the lim inf of Tn must be greater or equal than 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus etc. plus 1 over m factorial. Agree? And this is nothing else but the number Sm. So what do I know now? I know that the lim inf is greater or equal than Sn. So it's greater or equal than the limit of Sm. This is a trick when I'm taking m and n at the same time. And so my conclusion is that the lim inf of Tn is greater or equal than E, because this is what Sm tends to, and we showed previously that the lim sup of Tn is less or equal than E, and therefore the lim inf of Tn and the lim sup of Tn must be equal, and they're equal to E, and they're equal to the limit of Tn. Okay, so now you know the deep secret. Now you know why you had always been taught this little amazing fact that this particular sequence converges to E. The result of it is not in this particular sequence, but rather in the series 1 over n factorial. Okay, good? Okay, so let's do one other amazing fact about E. And so what I want to do is I want to say that this E, which is equal to the series sum of 1 over n factorial, n from 0 to infinity, which is equal to 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus etc. plus 1 over n factorial or k factorial plus etc. that this series not only converges, but it converges very, very, very fast. Well, what do I mean by very, very, very fast? I mean that if I look at E minus the nth partial sum of this series, so this will be 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus etc. 1 over n factorial. If n is 10, then the difference between E and Sn is very, very tiny. And let's try to prove this, because what I know is that this difference over here, so what is this difference? This difference over here will be whatever is left in E, right? Whatever it is left in this infinite sum. So it will be 1 over n plus 1 factorial plus 1 over n plus 2 factorial plus 1 over n plus 3 factorial plus etc. So this is an infinite series, and what I can do is I can say that this is the series is equal to, I'm going to factor out n plus 1 factorial, so it will be 1 over n plus 1 factorial, and then what will I have? I have here 1 plus 1 over n plus 2, right? This is because n plus 2 factorial is equal to n plus 1 factorial times n plus 2, and then I will have plus 1 over n plus 2 times n plus 3 plus etc. True. Now let me make this a little bit easier, and this will be less or equal than 1 over n plus 1 factorial times 1 plus 1 over n plus 1 plus 1 over n plus 1 square plus 1 over n plus 1 cube, right? That's because, for instance, n plus 2 times n plus 3 is definitely less or equal than 1 over n plus 1. 1 over n plus 1 square plus etc. And what I have here is a geometric series, and I know what is the sum of those series. The sum of those series is 1 divided by 1 minus 1 over n plus 1, because the series is with respect to this particular number x, So this would be x squared, this would be x cubed, etc. Okay, and I have 1 over n plus 1 factorial in front of it. And now let's compute 1 over n plus 1. I hate arithmetic. And then you will have 1 divided by n plus 1 minus 1, right, divided by n plus 1. So it will be 1 over n plus 1 factorial times n plus 1 divided by n. And this n plus 1 factorial and n plus 1 factorial at the end will give me 1 over n factorial times 1 over n. Okay, so what we have proved here, we proved a very, very important and nice result. And the result here is that if I look at the difference between the number e minus Sn, this is greater or equal, strictly greater than 0, this is the n's partial sum, and this is less than 1 over n factorial times n. So what that means is that if you compute the first 10 terms of those series of the sequence of partial sums Sn, then you will have a very, 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 very good approximation to the number e. Okay, so here is an unexpected theorem that pops out of nowhere. It is not mine, it is actually written in Rudin, and the theorem says that the number e is irrational. Well, I'm sure you know that. You probably know that e is not only irrational, but it is also transcendental, and the proof that e is transcendental is a bit more difficult than the proof that e is irrational. So let's prove that e is irrational, and the proof is by contradiction. Suppose that e is rational. So suppose that e is equal to p over q, where p and q are integers. Good. So now what I'm going to do is I'm going to look at e minus s sub q. So this is the integer I'm talking about, and what that means is this will be, let's see, less than 1 over q factorial times q. Do you agree with me? Okay. And of course, it will also be greater than 0. So now let's multiply both sides of this inequality by q factorial. I will have 0 is less than q factorial times e minus sq, which is less than 1. Okay. Now what I claim is that q factorial times e is an integer. Well, why is that? Q factorial times sq is equal to q factorial times 1 plus 1 plus 1 over 2 factorial plus etc. plus 1 over q factorial. So if I multiply every one of those terms by q factorial, I'm going to get an integer. So my conclusion is that q factorial, remember, q factorial times e is equal to p over q, so that's an integer, and q factorial times sq is an integer, and the conclusion is that q factorial times e minus sq is also an integer. It is an integer which is less than 1 over q, that should have been q here, and greater than 0, so 1 over q is less than 1, so therefore this quantity, which is an integer, is between 0 and 1, and you all know that there are no integers strictly between 0 and 1, and this gives me a contradiction. Which completes the proof of the theorem. Isn't it cute? Let me just say one little bit, and that is the fact that the questions about which numbers are rational, which numbers are irrational, which numbers are transcendental is of great interest in mathematics. So what we are showing here is that E is an irrational number, and let me tell you something else about it. If I have any number, real number R, and if this real number written as infinite series, not as finite series, but infinite series, AK, and if this series converge very, very quickly, very, very, very quickly, but they're still infinite series. So if this is a finite series, the number is definitely rational, if AK is irrational. But if this is an infinite series and the numbers converge, and the series converge very, very quickly, then the number will have to be irrational, and moreover, it will be transcendental. Okay, just one more piece of, thought. You do know that E and pi are transcendental numbers. What about E plus pi? Believe it or not, we still don't know. Probably at least irrational. Is it irrational? Well, that's also an open question. So we cannot prove that this number is rational or irrational. Most normal people would believe that it's irrational, but there is no proof for it. Likewise, there is no proof that E times pi is irrational. What is true, and this is very, very easy to show, that both of them, cannot be irrational. Well, let's see. Why not? If I look at the equation x squared plus or minus e plus pi x plus e times pi, the roots of this equation is e and pi. E and pi are not algebraic numbers, so if both of those numbers are rational, then they cannot be the root of this equation, and therefore both of those numbers cannot be rational at the same time, but we don't know if either one of them is. We know that one of them has to be rational, but we don't know which one, okay, or both. One more comment about E, and then I will be done with E. So once again, remember that E is equal to 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus etc. plus 1 over n factorial plus and so on. All these numbers are positive, and therefore it is greater or equal than just 1 plus 1, which is equal to 2. Well, in fact, it is strictly greater than 2. So now we know that this number is greater than 2. On the other hand, if I look at the same number, and I can say that this is less than 1 plus 1 plus 1 over 2 plus 1 over 2 square, plus etc. plus 1 over 2 to the n, and this is 1 over 2 to the 0, right? So what will be this number? This is a geometric series, and they converge to 1 minus 1 divided by 1 minus 1 half, so that will be 2, and therefore E is less than this one, the first one here, plus 2, which is equal to 3, and this is why you all knew from childhood that e must be less than 3 and greater than 2. Alright, and this completes my discussion about the number e.